Okay, let's talk about lambda expressions and generators. So, what are lambda expressions? Well, we use lambda expressions to condense our code. So, it's used to condense one-line functions that obviously return a value. So, when we're talking about lambda expressions, it has to be one-line functions that return values. So, let's take a look at our function on the right. Def, which is used to define a function, calculates square, takes in one number, and returns that number squared. It's a very simple function, and we've seen these one-line functions before. And why do I say one line? Because there's nothing really going on inside the body of this function, right? We're just returning num squared immediately, so it's one line. So we can actually condense this and use lambda expressions. So if you look on the bottom, we have calculate square. Notice how we're making it a variable instead of a function, but it will be given a function type later on, is equal to lambda num squared. So you say, oh, this is very similar, which is true. It's very similar, but it also has its kind of own quirky syntax. So before we would have to define calculate square, put in the parameters in the parentheses, then we have to have the semicolon and then return. Here we don't have any return statement, we don't have parentheses, and we have this weird keyword lambda. But this is a syntax, so we have to say lambda. That's how you define that this is going to be a lambda function, right? And then what comes after the lambda is the input or the parameter that you would normally have. So in this case we have num, so lambda num. And then we put a semicolon like always. This is to tell that this is a different part of the code. And then we say num squared. So this is an implied return statement. So given this lambda function, it would imply the num squared to be returned from this lambda function. So we actually cannot say return num squared. That's not proper syntax when dealing with lambda functions. So we just say num squared after the semicolon. And if we say x is equal to calculate square of 25, notice how we're calling calculate square with the parentheses because it's a function, right? So even though we're kind of defining it as a variable, it's given a function type because of the lambda. So we call it with parentheses after and provide the number, which is called num. And x after this case would be, what, 625, right? So let's talk about the syntax again. Lambda is the key word that you have to use, right? You cannot switch this up. You cannot put it uppercase. It has to be lambda all lowercase because that's the key word. The parameter goes right after, before the semicolon, but right after the lambda keyword. And finally, we have the return, whatever is going to be returned after that, after the semicolon. So we don't specify return, but we say colon num squared in this case. Okay, so you might be wondering, what's the difference between a lambda function and normal functions? Why do I have to use this weird syntax with my lambda function when I'm so used to the def function name parameter syntax, right? But there's actually a pretty big difference. Lambda functions are meant to be anonymous. So they're meant to be used anonymously. And you might be saying, what is that? But being used anonymously means that you don't actually have to save it in memory, right? So in this case, this kind of defeats the purpose. And I'll talk about that in a couple seconds. But we are assigning this function to a variable, and then that can be called using the function syntax and so on. So it does defeat the purpose, but I'll talk about why lambdas are so useful. Once we're done using a lambda in certain scenarios, we don't use it ever again, right? You might have a case that where you want to use a function that you don't use ever again. So with that, you don't have to save it in memory, right? If you save it in memory, you're letting go of performance. So lambda functions are used with other type of functions called map and filter functions, which we'll explain in just a minute. But they're used in these other type of functions to do powerful processing on data, but also get rid of after you're done with that processing. So that's the whole entire point of lambdas, to be used anonymously and to be basically rid of after you're done using it. So let's talk about these special functions that use lambda expressions. So look at the map function. This is a more higher level Python concept. So the map and filter functions, those are higher level Python functions. But let's take a look at what's going on. We have a function called square, and just like before, we calculate the square. We return the square of the number provided. And then we say I have my list, which is 1, 2, 3. And then we have this weird syntax. My list is equal to list map square list. So we're taking the map of square and then list, my list, and we're converting that to a list. So you don't have to look at the conversion to a list, the casting to a list, because that has to be done because a map does not return a list, it just returns a special map object, which needs to be converted to a list. But if you take a look at the map function, notice how we're passing in square and we're passing in my list. So what the map function actually takes in as parameters, it takes a function and it also takes an iterable. So an iterable is anything that can be iterated over through, right? So it takes a function, which is square that we provide, and it takes an iterable. Then it applies the function on every single element in that iterable and returns the new iterable, if that makes sense. So if you look at the my list, it's 1, 2, 3. It performs square on every single element in my list and returns a new map object of that iterable. So in this case, it returns a map object that somewhere contains 149. So when we convert it to a list, it actually returns a list that contains 149, which is important. So, which is what we want, basically. So the list is just converting it from a map object to an actual data type that we could use. But the map object, the map function is the special type of function that takes in a function and also takes in an iterable and returns a special map object. So you might be wondering, where does lambda functions come in? So first let me talk about filters actually, and then I'll cover lambdas. So filters, just like map, you actually see many similarities between filters and map. They take a function, they take an iterable, they return a special object, and you must convert that object using, if you want a list, you must convert it to a list using casting. So let's take a look at what's going on. Here we have def is even, takes in a number, and it returns if the number is even. So this is special syntax. We're just taking the modulo of number with 2. So modulo, so number modulo 2. If that equals 0, we can be certain that that number is even, right? Because if it's any other number, so let's say odd, it has to be odd if it's not even. It will be 1, right? So it will be false. So in that case, number %2 is equal to 0. That will always return true if the number is even. Now here we're saying filter, we're passing this is even function, and we're passing in our iterable. So what filter does, just like map, it goes through the iterable and performs the function passed in every single time on every element. So we have 1, 2, 3, 4, and it performs is even on every element. But the key difference between maps and filter, so if you see map, that just returns everything, right? It returns the same size. We have my list is 1, 2, 3, and my list after the map is still 1, 2, 3, because map is just performing operation on existing data. What filter does, as the name suggests, it filters through the iterable to get the important values we want. In this case, we want just the even numbers. So what we do is take in my list and take in is even. And what filter does, it applies the function to every object or every element. So let's start at 1. It goes at 1. If we pass 1 into is even, we get false, right? because 1% 2 is 1. Now, if it's false, filter just ignores it and goes on to the next one. So we have 2 now. 2 modulo 2 is 0. So we get true. So now filter adds that value. It keeps that value in mind. And we go to 3. 3% 2, 3 modulo 2 is 1. It skips over that. We go to 4. 4 mod 2 is 0. And then we finally add that as well. So in the end, we get 2 and 4. And here we separated the casting and the actual filter function into 2 different lines. So here we did it in 1 line, but it's the same thing. We're just taking my filter, and then we have to convert that to a list because my filter or filter is a special function and returns a special object. So we're converting my filter, which is a filter type object, to a list that we can actually use it later on. So that was the filter function and the map function. Now where do lambdas come in? So if you look at this, there's a lot of things going on. Let's just talk about this. In the previous examples, we used functions that were one-liners, right? Did you notice that? In the square, we just returned num squared. In the is even, we just returned number %2, number mod 2, if it's equal to 0. These are just one-line functions, right? There's nothing in the body that's more complex. It's just one line. So we can take lambda functions. We can take advantage of lambda functions. So in this case, let's take the map function. We pass in my list just like before as a second parameter because that's what map requires, and filter. And notice the function, instead of whatever it was, calculate square or square, we pass in a lambda function. So lambda functions, as the name suggests, they can be used as functions, wherever functions are, if it's possible. So lambda num, we take in a number, and then we return number squared. So we've already covered the syntax and why that works. So just like the normal map function, it sees a function, it applies that function on every element in the list, and then we finally get our product. So we would have to convert this to a list, and we would have a list that have all squared numbers. And the same thing for the filter. We have lambda num, and then we're finding if num mod 2 is equal to 0, if we're finding if it's even, and it applies that function to every element in the list. And if it returns true on any element, it keeps track of that, it adds it to its own values, the collection of values it has, and then we have to convert that to a list, and then we can use that later on in our code. But you know one key difference. After we use this filter function here and the map function here, we're kind of left with the square and the is even functions, right? We're left with this. We can't like delete them now in our code. So what do? Lambda functions just automatically get rid of themselves after they're being used. So that's important, right? After this map function, let's say we don't need this square because it's such an easy function, right? We don't need this square function anymore in our code. So in this case, we would be stuck with that. But in this case, it automatically gets rid of, because we don't really specify a name for this, right? What's the name of lambda num squared? What is the name? There's no name, right? We're not assigning it to a variable. We're not doing anything like that, which is why I said that the previous example, this was kind of defeating the purpose. Here we are assigning it to a variable, so it does keep it in memory, which is not really the point. But in this case, we're just using it for the single purpose of the map function. Once the map function is done using the lambda function no longer exists, right? So it's taken out of memory because we don't need it. Now, what are the limitations and when to use lambda functions? Lambda functions are especially good with map and filter functions. So when you see map and filter functions, you would most likely be using lambda functions if your logic is not extremely complex. So the main problem with lambda functions is you can't really simulate complex logic. So in this def, sum of numbers. Yes, we do take in a number just like before, but look what we're doing here. We're creating a variable called sum. We're iterating in a range, and we're adding sum, incrementing sum by whatever number I is. We're returning sum. So this kind of logic is more complex, right? It's not the most complex, obviously, but it's more complex than just one line. Here we're actually having a for loop in here. We're instantiating a variable, we're declaring a variable. So you can't simulate this with Lambda functions. So that's the problem with this. If you could, it would look really weird, but you can't, because these are just one-line functions, right? Lambda num, we return num squared. Lambda num, we return num %2 is equal to 0. At the end, let's go back. Sorry about that. But you can see how it doesn't really make sense to use lambda functions when we have all this complex logic, right? So when you do have this complex logic, it's actually not really possible to use lambda functions. So lambda functions, again, they're used for one-line functions that can easily be expressed, in one line. Now let's talk about generators. So this was a two-part presentation, talked about generators and lambda functions. So we covered lambda functions, let's talk about generators. Generators are used to efficiently generate a list of values. So yes, that's a kind of vague definition, right? We use generate in the definition, but it's pretty simple. They generate values on the go. So instead of storing a lot of values in memory, just like a list, when you have a list, you're storing every single element in that list in memory, right? So instead of doing that, generators calculate values based on a set principle, set algorithm on the go. So every single time you need a new value, a generator will generate that value instead of having to keep all the possible values in mind or in memory. So let's say we want to print out the first million numbers, right? We could do this. We could have a for loop. We can append the million numbers to a list. We could have a list of million items and then print that list out. We could do that, right? But generators help us generate these numbers on the go. So what if we use a generator in this case? And you might be saying, why can't I just do for I in range of whatever number, the million, print I? And yes, we'll get into that, why that's efficient. So, but in this case, if you just have a list of million items, you'd be storing all million items in memory, which is not the most efficient, and it definitely is most definitely memory intensive. So you want to make your code as efficient as possible, and using generators is just one way of doing that. So let's look at the range function. So you might have said, oh, I can just do what I have here, right? Well, yes, you can. That's exactly what we want you to do. So the range function is a generator. So many people aren't used to this. Many new beginners, they don't know that the range function is a generator, but it is. So it actually, behind the scenes, what it does in the function, it generates those values. And we'll talk about how you can actually generate these values and how Python lets you do that. But in the behind the scenes kind of aspect of this range function, the range actually generates new values as it goes. So what it does, it keeps track of the current number and the step size, right? That's what the range function takes in, the current number and the step size. And then it calculates the next number. So we specify that this is on the go. This is whenever we need it. So for I in range of 10,000, I starts at 0, right? And then we print I, and then the for loop requests the next element of this range function, and then we get the next values, which would be 1, 2, 3, etc. So let's talk about the behind the scenes of generators. Like, how do you create a generator in Python? Well, the main difference, actually one of the only differences versus from a generator and a normal function, is the yield versus return keyword. So when you have a normal function, take a look at squares, we have a list of results, right? Then we do for I in range of num. Notice the range generator. So this is still a little efficient, but not quite, because we're appending I squared to a list and we're returning the list. So only when the for loop is done does the list get returned. And that could be intensive, right? What if num was 10 million? Then we would have to append 10 million, and not only that, we would have to append that number squared. So results would actually contain all numbers from 0 to 10 million squared, which is a huge number, and that would be memory intensive, right? That's not efficient at all. And it'd actually be pretty slow program if we try to iterate over that list. So yes, after this you could say for I in range or for I in squares, right? Because squares is a list, or squares, the return statement is a list. And you can do it like that, but that's not really efficient. When we use a generator, on the other hand, instead of return, we use yield. Also, look how less messy generators look than normal functions. So we don't have any variable called result. We don't have a return statement. We're not appending anything. All we're doing is saying for I in range of num, yield I squared. So we're saying whenever we get to the yield statement, Python would basically return that statement to where it originated from. And then whenever a special type of function called next, which I'll talk about in a minute, whenever next is called on this generator, it would look for the next value. So let's take a look at that. So by using yield in a function, we create a generator. So that's the basics of creating generators. We use yield. So Python will generate the squares, in this case, since we're doing I squared, of the numbers on the go and yield them to the to where it was called. So how do we use our custom generator now? We created our generator. How do we use it? So we can use it just like the range function, right? We're saying for square num in squares. So you might be saying, oh, squares does not return a list, so how can I iterate that with like the in keyword, right? We're using in. But we can, because this is a generator. So for square num in squares, let's take a look. The first iteration, what is I in squares? I would be 0, right? So we yield I squared, which would be 0. And I think we showed here. Yeah. We yield I squared, so 0 squared, which is 0, back to the destination of the for loop. So now square num in the for loop, if you see right here, square num is 0 on the first iteration, and we print 0. Then Python calls a next function, so a special next pre-built function on the generator, so next squares. Squares is now for I in range of num. Now I is 1, right? So it returns 1 squared, which is 1. And then we print out 1 because square num is 1. This happens so on till 10,000. But notice that we don't keep all the values in memory. We only keep the current value, the previous value, and we use those two values to determine the next value. So that's all you do. You keep a track of the previous value, the current, and we use it to determine the next. And let's talk about the efficiency of generators. Generators are super efficient when you're dealing with large size collections. So if you're dealing with lists of, or if you're dealing with numbers that contain, or if you're dealing with 10 million numbers, millions of numbers, using generators wherever possible is the best way. So, yes, so we said this functionality is useful when using large sets of predictive numbers, and we'll talk about what that means in a second. We have to use predictive numbers or other types, so predictive strings, predictive tuples, whatever. Anything that's predictive in nature, you can use generators. and it would technically be more efficient. It would definitely be more efficient, actually. So let's talk about the limitations. So we talked about predictiveness, right? Generators must be predictive. Since they only store one value, basically two actually, the previous value counts, at a time, you could not use all previous values to determine the next value, right? Let's say if you're doing a list, let's say you have this algorithm that calculates numbers. In each next number is the sum of the previous numbers. So let's say we have 0, and then we calculate 1. So we keep adding 1, and then we take the sum of the previous numbers. If we have that, we can't use generators, right? Because we're only keeping track of the previous number and the current number to predict the next number. So if we're kind of discarding all previous numbers from memory, we can't really use generators there. So that's why in complex algorithms that require past history to affect or influence new values, we cannot use generators. So there is a limitation to generators, which is they have to be predictive. So you must be able to basically calculate all the values beforehand, before even running your code. So in this case, for I in range of, let's say, 10,000, we know what every number of I would be, but this is just more memory efficient because we're not actually calling any return statement, we're not keeping everything in memory. So that's the efficiency of generators. And we just put something on the side. We showed how in generators, they return, obviously there's a special, they're a function, right? So you must convert that to a list, but that also defeats the purpose because if you're dealing with lists, you're dealing with every single element in memory. So kind of using lists with generators, they're not the best, they don't go the best together. So use generators when you have predictive values and you can save a lot of memory and efficiency in your code. So that was it. We talked about generators and Lambda expressions. The Lambda expressions used filter and map functions, the filter and map functions use Lambda expressions and so on. So we talked about a lot of things. I would definitely review these Lambda expressions and generators in the future because they're much more higher level Python concepts. And if you know these, you'll be a much better Python programmer. So that was it for now. We'll see you next week.